Good evening, everyone. I see here a question. Good evening, sir. What hypervisor did you say you use? Hypervisor in terms of what? Oh, virtual machines. So my hypervisor that I prefer using for virtual machines is VMware Fusion. Pleasure. So how is everyone doing this evening? I'm also well, thank you. So why are you guys tired? Long day? I didn't have a bad day. I was at the observatory most of the day. So I see we are only 45 people online, so let's wait another minute or two for more people to join us. So it's always fun being at the observatory. So that's where I spent the majority of my time. So if I went into the observatory today to sort out some issues with a supplier for equipment and also for my own research. What's printing in the background? Just a few documents that my girlfriend is printing. So for my research, I work in astronomy in a field called spectroscopy. So in spectroscopy, we're going to learn about spectroscopy in this module as well. But in spectroscopy, you basically look at the different composition of objects in space. Because we know certain elements emit certain frequencies. So let me rephrase this. Certain elements emit certain frequencies and certain elements absorb certain frequencies. So with this, we know, for example, methanol, for example, is emitting microwaves at roughly 6.6 gigahertz. So we know if we see the frequency 6.6 gigahertz in space, it has to be methanol. So that's what spectroscopy is. So we know certain elements radiate energy at a certain frequency and certain elements absorb frequencies and radiation at a certain level. So that's called the emission absorption spectrum. So my research is to find better ways to do spectroscopy. So to find better techniques and methods to do spectroscopy and to create emission absorption spectrums. So spectroscopy forms a big part of astronomy. We use spectroscopy in normal optical astronomy and in radio astronomy. So I think this is long enough, so we can start with the lecture. Before we start with the lecture slides, regarding your moon assignment, so what you are supposed to see with this assignment, let me show you a image of what you're supposed to see. So with your moon assignment, this was you're observing for 10 days, meaning you're going to see a third of this image, depending on where you are in the moon cycle. But remember, the moon is in a 28-day cycle. So this means you'll see a third of this pattern for your assignment. And this is called Almena. So let me show you another image of this. So analemma, tongue twister. So depending where you are in latitude on Earth, you will see it at a different angle. But this is more or less what you guys will observe, but only a portion of this. So when it's new moon, you won't be able to see the moon, but is there. But you will see this figure 8 or infinity sign. So it all depends where you are in latitude, longitude, and where your location is on Earth. For example, this is from another place. All by like this. All like this. But this is in essence what you will see. And this is called a analemma. And the sun does exactly the same thing as well. So just for this is something interesting to show you guys, and what to look out for your assignment. So by sketching everything, you will sketch a third of this depending on which date you select for your observations. And then you need to write an article about this, telling me what you have learned, what have you observed, what is the physics behind everything, and what is the astronomy behind everything. So if we observe the moon for the full 28 days, could we do a write-up on the full analemma? Yes, you're more than welcome to. If you have the guts to do the full 28 days, you are more than welcome, but please take note, for the assignment, you only is necessary to do 10 days. But if you want to do 28 days, you're then more than welcome to. All depends if you have the time for it, but 10 days is enough and sufficient. So, let's go to our lecture slides. Yes, you can start at any time of the month. So just check the moon rise and set times. You can just Google it. So you'll see the moon rise and set times moves on by 40 minutes every day. So please make sure the date and time you are selecting corresponds to a time where you are actually available, that you can see the moon, and that the moon will also be high enough to observe. Because I know out of previous years, that is where most students make a mistake. They pick the weird time without doing any research. And then halfway through their observations, the moon is suddenly below the horizon and they can't see the moon at their selected time anymore. So in the study guide, I've selected, I think, the 14th. It's a good day to start because you will see the moon rising in the west, and that will become later and later and later. After my west to east, you'll see that become later and later and later as the days goes on, but you're more welcome to select any date and time. So before we start off with our lecture slides, I thought of showing you two videos of two telescopes. So the first is of SALT, the South African Large Telescope. So have any one of you visited SALT before? So SALT is in Sutherland. So it's a very, very, very little town. So it's a great place to visit, even for a holiday or a long weekend. I've spent some time at SALT. An amazing place. Accommodation at SALT is also dirt cheap, so it's a very nice breakaway if you can get there. But let me show you a short video of SALT.
Welcome to Sutherland, South Africa. This is the site of the South African Astronomical Observatory, and it's the premier site for optical astronomy in the country. The observatory was established 40 years ago and is at a position which is excellent climate for astronomy, with many clear hours per year, and also in a very, very dark site. It is also the site of the Southern African Large Telescope, a multinational project which was completed in 2005, and science operations began in 2011. So SALT is located with about 20 other telescopes on this small hill in the Karoo. It's about an altitude of 1,800 meters, and it's in a region which is very underpopulated, with no major towns or cities anywhere nearby, which means there's no light pollution here. So the skies that we have in Sutherland are some of the darkest that you'll find anywhere on Earth. And that's obviously one of the main reasons for locating the observatory here near Sutherland. The other reason is that it's in a region between the two main weather systems that affect South Africa. The summer rainfall comes up in the northeast of the country, and the winter rains come with cold fronts through the Cape, and Sutherland straddles that and often misses the weather associated with that, which means we have a lot of clear nights in a year to be able to do astronomy. From about early afternoon, we begin to air condition the inside of the dome so that by the time we open up at the beginning of the night, the temperature inside is pretty close to that of the outside temperature. This is to avoid air currents, which can cause distortion of the images and make them blurrier than they would be otherwise. And these louvers that open up during the evening also keep the building ventilated to ensure that the temperature inside and outside are in equilibrium. So this is the telescope, and what you can see here is the heart of it, which is the primary mirror array. It consists of 91 individual mirror segments, hexagonal in shape, and they're roughly 1.2 meters in size. They're all in a spherical configuration, and they're aligned to behave as if they're one single, effectively 10-meter diameter mirror. These mirror segments have been taken out of the telescope for cleaning and recoating, a process that we do throughout the year, typically twice a week, so that we keep the reflective coating in the telescope at maximum efficiency. So the interesting aspects of this telescope is that it's designed such that the altitude direction, the up and down direction of the telescope is fixed, which is something which keeps the cost of the telescope and the complexity of the engineering much simpler. The cost of this telescope is typically at about a fifth of the cost of a conventional telescope, which would have the varying altitude as well as azimuth, and having to factor in the changing gravity, which causes different forces on the telescope. So the fact that it's a fifth of the cost, but still able to basically observe 70% of the southern sky, made it a compelling design for South Africa to keep the costs down and yet still have the capability of a large 10-meter class telescope. This design was pioneered by a telescope in the United States called the Hobby-Eberle telescope, and then it was the basis of the design for SALT. So the way in which this telescope operates is that it can move in azimuth, which is rotating left-right, to anywhere, and then acquiring the target to observe. And so to track the object as it moves across the sky due to the Earth's rotation, there's a tracker right at the top there near the focus of the telescope called the prime focus. And that is what's used to track the object as it moves from east to west. We can see here the prime focus payload mounted on the tracker. So all of the instrumentation, all of the optics, guide cameras, calibration systems are all inside this unit. It weighs about 2 tons, and it has to move very accurately to follow an object during an observation. So it's mounted on this tracker beam, and it can move up and down the tracker beam in the Y direction, and the whole tracker itself moves left and right in the X direction. In addition, it has to move up and down to keep the object in focus, and also rotate to counter the rotation on the sky as the object is being tracked. You can also see here these triangular legs, which are hexapods, which are extendable legs that can tip and tilt the payload so that the optical axis of the whole system is always on a radius vector of the primary mirror. At the top here, you can see the main workhorse science instrument for the telescope, which is the Robert-Stobie spectrograph. It consists of a variety of different gratings to do different dispersion spectroscopy. It has a set of filters, and all of these can be interchanged automatically in the control room by the astronomer to configure the instrument for observations for different programs.
These are 2 Fabry-Pro etalons of the same sort that are used in the Robert-Stobie spectrograph on SALT. These 2 etalons here are actually designed for a different, smaller telescope, so they're smaller in size in each dimension by about a factor of 2. So you can imagine that the etalons on the SALT telescope are much bigger, much more massive, really spectacular pieces of optical engineering. There are 2 different spectral resolutions. The first of these etalons has a resolution, a so-called high-resolution etalon, with resolution of about 10,000. It's used for absorption and emission line work primarily in stars and star clusters. The other etalon has lower spectral resolution, around 2,000, appropriate for the work that we do in measuring the motions within galaxies. These etalons are on a light box, and what we're seeing when we look into it are the emission lines from the fluorescent lamps below, and that's what produces the colored rings. When they're in use on the telescope, these electrical connectors over here are connected to a controller that stabilizes the etalons in both tip and tilt and spacing, and it can control all of those motions to about 10 atomic diameters. These are really spectacular pieces of engineering and electronics.
Also in here is the acquisition camera and the high-speed imaging camera, Salticam. There's also a fiber feed where the light can be sent down optical fibers down to a very stable spectrograph in the spectrometer room below the telescope. There are a total of 16 optical fibers that droop down through below the primary mirror and down into the spectrometer room, about 40 meters, 45 meters in length. So we're now in the spectrometer room, which is underneath the telescope, and it's a circular room inside the actual pier of the telescope on which it rests. And inside this room, we have this black rectangular structure or enclosure, which has the high-resolution spectrograph inside it. The way it works is that light is focused into optical fibers at the top of the telescope and end up coming out through this circular hole in the ceiling, which is in fact the center of the rotation bearing of the telescope about which it rotates. And this black cable that you can see coming down has all of the optical fibers that take the light from the telescope and into the spectrograph. So this is where the electronic controls and various other things like the detector cooling system, the vacuum pump for the spectrograph are situated. The spectrograph itself is inside this door, which is inside the main room. But because we want to keep this very stable in temperature and constant, then we don't allow people to walk in and out of the spectrograph room. There's no need to, in fact, because the whole instrument is inside a tank, completely sealed, and then covered in this sort of polystyrene insulation material, which is covered all the way around the vacuum tank to keep the temperature at a very constant level. So in the control room is where the operator and the astronomer run the telescope during the night. So the operator is in charge of pointing the telescope to the respective targets. The astronomer chooses which targets to observe from the list of different programs which have been accepted for the telescope. So in front of them they have the ability to choose the instrument configurations, choose the targets, conduct the observations, and also to analyze the data and see the initial reductions of the data. In addition, they're able to monitor the outside conditions. They have a set of weather instrumentation which can tell the astronomer what the conditions are like, and that will determine really what the sort of programs that they will undertake in a given night.
That is pretty cool, right? So I see a question about the hexagonal lenses, and there is basically a short answer to it. So if you think about surface area, what is the surface area or the figure that will give you the biggest surface area and is the most simplistic in form? So that would be a circle. Yes, you are correct, Mr. Melville. So just to make your example correct, so this is a circle. So let, for example, we can say, for example, the lens was square. So that means the square area is still smaller, meaning we are losing pieces of surface area that we could have actually used. but it is very difficult and very expensive to create one big giant mirror. So now, say for example, we do the same thing, and we want a big circular mirror. And if we use circular mirrors inside, then again you will see there is gaps between the mirrors. So how do we optimize these gaps in between? We create hexagonal mirrors, and with a hexagonal shape we can create one big circle, and that is why the mirrors are hexagonal in form. So then the second video I want to show you guys is my favorite observatory. So I've spent a lot of time at this observatory before, so you can almost call it, I would, my favorite is observatory, and that's the Green Bank Observatory. So let me show you a video of the Green Bank Observatory.
GBT is the largest fully steerable radio telescope on the planet. It's one of the largest moving structures on land. It stands 485 feet above ground level, which makes it taller than the Statue of Liberty, weighs almost 17 million pounds. So with 16 wheels, more than 1 million pounds per wheel is transferred to the foundation. Like a bigger bucket collects more raindrops, the GBT's large surface area can collect more radio waves from space. The reflecting area is 2.3 acres. So a football stadium would fit inside of that.
So radio telescopes are just one window onto the universe. So when you think about astronomy, often people will think about your classic optical telescope, something you can stick your eye up to and you can look through and you get to look at a picture of a galaxy. A radio telescope is the exact same idea, only instead of looking at the optical waves, the stuff that you can see with your eye, it's looking at radio waves.
We're trying to take the principles, the things we understand about chemistry from the laboratory, and apply those to molecules in space. Understand how you can build up things that lead to the formation of maybe life, from what we see starting out in the earliest remnants of dead stars and the birthplace of solar systems.
The light coming from the galaxy we're looking at is about as old as the Earth is now. The GBT is especially good for this. It's so massive, its beam is very small, it's incredibly sensitive for this kind of work.
The sensitivity of the GBT is 10 to the minus 29 watts per square meter per hertz. Now, to put that in a term that you can understand, it can detect an energy level that's equivalent to the energy given off by a single snowflake hitting the ground. A typical quasar in space gives out a billionth of a billionth of a millionth of a watt. So it takes very sophisticated and very sensitive receivers to detect those signals and be able to process them in a manner that the astronomer is needing.
How many kids haven't looked up at the sky and just said, what's up there? And astronomy is able to talk to them about that and keep that curiosity going. So that kid who is curious about astronomy may turn out to be the next best physicist. They may turn out to get a Nobel Prize solving something in medicine. But it all started because there was somebody willing to answer their questions about what's up in the sky.
So that is pretty cool. So that is my favorite observatory. I've spent a lot of time at this observatory in the past. And if you guys are ever in the United States and in the area or in the state of West Virginia, please go visit a GBT if you have ever a chance in your life to do so. So let's continue with tonight's lecture. So let me open up our lecture slides. A little bit more back. So last night we finished off with the Sophia Observatory. Yes, everyone's still awake and everyone still hear me. Okay, cool. So for tonight, we are going to look at high energy astronomy. So like infrared emitting objects, gamma rays, X-rays, and ultraviolet sources in the universe are difficult to observe because the telescopes must be located high in Earth's atmosphere or in space. Some high-energy astronomy satellites have been general-purpose telescopes that can observe many different kinds of objects. The largest X-ray telescope to date is the Chandra X-ray Observatory. Chandra operates in an orbit that extends a third of the way to the Moon. Focusing X-rays is difficult because they penetrate into most mirrors. So astronomers devise cylindrical mirrors in which X-rays reflect at shallow angles from polished inside of the cylinders to form images on an X-ray detector. Chandra Observatory has made important discoveries about everything from star formation to monster black holes in a distant galaxy that will be described later in chapters. This is how the detector will look like. So X-rays that hit a mirror at grazing angles are reflected like pebbles skipping across a pond. This X-ray telescope mirrors, like the ones in Chandra, are shaped like barrels rather than dishes. So this is actually quite an interesting point. Like I said, it's important, the design of a telescope. So if you would just have a normal mirror, the X-rays, depending on the material we will use, will just go through the mirror or will be reflected off the mirror and just bounce off. So to get actually everything to focus, our mirror is these cones, and these cones will focus the X-rays that it falls onto our detector. Speaking about this, do you guys know what the inside layer of an astronaut's spacesuit is made out of? Yes, Mr. Henning, you are correct. It is gold. There's a layer of gold inside a spacesuit because gold blocks most radiation we know in space. So to block and shield the astronauts from harmful radiation from the sun, the inside layer, so inside the spacesuit is a thin layer of gold that protects the astronauts, and that's why spacesuits are so expensive. So one of the first gamma ray observatories was the Campton Gamma Ray Observatory, launched in 1991. It mapped the entire sky at gamma ray wavelengths. The European International Gamma Ray Astrophysics Laboratory satellite was launched in 2002 and has been very productive in a study of violent eruptions of stars and black holes. The Fermi Gamma Ray Space Telescope, launched in 2008, is capable of mapping large areas of the sky to high sensitivity. So here we can see adding liquid nitrogen to the camera on a telescope is a familiar task for astronomers. Astronomical cameras with array detectors must be cooled to low temperatures to operate properly. And that is especially true for infrared cameras. And the reason we do this is the electronics we have in our detectors causes noise in the image. So to get rid of these electronic noise, you need to cool your electronics down to as close as absolute zero as possible. So we at Hardrow, we cool our receivers and equipment down to about 12 Kelvin. That's almost minus 260 degrees. The Green Bank telescope cools their receivers down to about 4 to 6 Kelvin. And we do this by, so the outside, so around our equipment, there's a small chamber. And that chamber is filled with liquid nitrogen. That liquid nitrogen cools our equipment, and our equipment is also, so we have vacuum pumps that constantly pump liquid nitrogen through the system to keep everything cool. Do they also add liquid nitrogen because the camera heats up a ton? So the camera heats up, yes, because if you use electronics, it will heat up. But the main idea is in optical astronomy, that's the heat coming from the camera that causes obstructions in infrared. But in radio telescopes, the electron flow within the equipment causes noise. So that's why we also cool everything down to as close to absolute zero as possible. So one thing about cooling things down is Eskom hates us for cooling down our equipment because it uses a lot of power. But to do astronomy, we need to do it. And one thing else is, these astronomies can never go offline. So for example, so does the liquid nitrogen not evaporate away very quickly? Because it's in a vacuum chamber, so it doesn't evaporate very quickly, and we pump, so the heated liquid nitrogen we get out of the system, we cool it down again, and then it gets pumped through the system again, so it's entirely a closed system. And like I said, our astronomy and other astronomies cannot go down for 1 second. So for example, the Hartebees-Hoek telescope, we are currently scheduled 18 months in advance to do observations on the telescope. The Green Bank telescope is, as I think now, currently 24 months booked in advance. If you want to use the Chandra Space X-ray telescope, it's now 36 months booked in advance. So we have redundant on redundant systems. So we have backup generators for our backup generators, big UPS systems. So our entire site is operational 24/7 and never goes down, except on maintenance days. So just looking through a telescope doesn't tell you much. A star looks like a point of light. Planet looks like a little disk. A galaxy looks like a hazy patch. To use a research telescope to learn about a universe, you need to carefully analyze the light the telescope gathers. Special instruments attached to these telescopes make that possible. And do you guys know what these instruments are? Any ideas? Really have no clue. Okay, so let's look at a few of these astronomical instruments we put on our telescopes. So just looking at the photographic plate. So the photographic plate was the first device used by astronomers to record images of celestial objects. Photographic plates can detect faint objects in long time exposures and can be stored for later analysis. Brightness of objects imaged in a photographic plate can be measured, but only with a lot of hard work that yields just moderate precision. Astronomers also built photometers, sensitive light meters used to measure the brightness of individual objects very precisely. So these photographic plates, you can think of it as basically X-rays. So if you get your X-ray back, entire X-ray is dark, and where your bones are on an X-ray, it is a lot lighter and you can see where your bones are. The photographic plates had the exact same principle. So the entire plate is dark, and then where light hits the plate, it creates an imprint, and the brighter the object is, the brighter the imprint is. And that is photographic plate. That was used at the end of the 1800s, beginning 1900s. And that was replaced by CCDs that we can talk about now, and also with photometers. So is that like a pinhole camera? Not really. So let me see if I can quickly get you an image of a photographic plate. Let's see if I can quickly get an image of a photographic plate. Let me quickly download the image and I'll show it to you guys. There's another image. Let's get one more final image. This will do, so I'm quickly just uploading them to Blackboard Collaborate. So how long is exposure time? So it all depends on the light from the object we're observing and how faint the object is. So the exposure times can be anything within a few minutes up to a few hours. Okay, so the images are being uploaded. Okay, just hang in one more minute while the photos is finished being uploaded. Okay, got it. So this is how a photographic plate would look like. So you see it is one big dark plate, such as an X-ray. And once you put it to inside the focus area of your mirror, so you add this as your instrument, it will create an image of what we are actually observing. And depending on what we're observing and the exposure we are looking at, so meaning how much light received at a certain time. Sorry, this is the wrong one. Where's that image now? This one. Then we can actually get nice pictures. So this is an image of the Andromeda Galaxy. And that is basically photographic plates. So how did I protect the plates from getting damaged by everyday light? So after the plates has been exposed to a light source, they are treated with a certain coat on top of it. I'm not sure what a coat is made of, and that will stop from normal light interacting with these plates. But this is how astronomers used to do it back in the day. So let me open up the slides again. Where were we? And we were here. But now in present day, we use charged coupled devices, or you will better know them as CCDs, as both image recording device and as photometers. The CCD is a specialized computer chip containing millions of microscopic light detectors arranged in an array about the size of a postage stamp. CCD chips have replaced photographic plates because they have some dramatic advantages. CCDs are much more sensitive than photographic plates and can detect both bright and faint objects in a single exposure. Also, CCD images are digitized, meaning converted to numerical data. This can be stored in a computer's memory for later analysis. Although astronomy research CCDs are extremely sensitive and therefore expensive, less sophisticated CCDs are now part of everyday life. For example, the camera on your phones makes use of CCDs. Infrared astronomers use array detectors that are similar in operation to optical CCDs at other wavelengths. Photometers are still used for measuring brightness of celestial objects. Astronomical images are often reproduced as negatives, with the sky white and the stars dark. That makes the faint parts of the image easier to see. Astronomers also manipulate images to produce representable color images, also known as false color images, in which the colors represent different aspects of the object, such as intensity rather than visual color. So here we can see an image A. The astronomical image can be manipulated to bring out difficult to see details. The color photo of this galaxy is dark, and the dust cloud and the galaxy's central plane do not show very well. Then image B. The negative image was produced to show the dust clouds more clearly. So right here we can see a typical weather map uses contours with added color to show which areas are likely to receive precipitation and what type of precipitation you receive. So in image B, we can see a radio image of Tycho's supernova remnant, the expanding shell of gas produced by the explosion of a star first seen on Earth in 1572. This image, represented by color code, shows intensity of radio radiation at just one wavelength. Then in image C, a picture of galaxy M101, composed of a visual wavelength image from the Hubble Space Telescope, combined with an X-ray image made by the Chandra X-ray Observatory, plus an infrared image from the Spitzer Space Telescope. In this representative color image, the blue shows X-rays from the hot gas heated by the expanding stars and the black holes, whereas the red shows infrared emissions from cool, dusty clouds of gas in which stars are being born. So you guys are all happy with these false colors. So the easiest to explain it is with this radio image. So here we can see the more brighter the color, the more intense the radio waves. Here we can see the blue is the X-rays and the reddish is the infrared. So you're all happy with this explanation. Awesome. So now we get to spectrographs. So spectrographs is where my field of research is, but my spectrographs are on radio telescopes rather than optical, but the process is exactly the same for both. So to analyze light in details, astronomers spread out the light according to wavelength, so in color, a function performed by a spectrograph. You can understand how this instrument works if you imagine repeating an experiment performed by Isaac Newton in 1666. Newton bored a small hole in a window shutter of his room to admit a thin beam of sunlight. When you place the prism in a beam, it spread the light into a beautiful spectrum that splashed across his wall. From that and related experiments, Newton concluded that white light is made of a mixture of all the colors. Almost all modern spectrographs use a grating rather than a prism. A grating is a piece of glass or metal with thousands of microscopic parallel grooves scribed into its surface. Different wavelengths of light reflect from the grating at slightly different angles, so the white light is spread into a spectrum. You have probably noticed this effect when you look at the closely placed lines etched into a music CD or DVD. As you tip the disc, different colors flash across the surface. So the spectrum of an astronomical object can contain hundreds of spectral lines, dark or bright lines that cross the spectrum at specific wavelengths. So here is the Hartog or Hartebees Hoek telescope, where what I'm using for my research and where I am most of my time. So here we can see there is 26 meters in diameter. Here in the back we can see our 15-meter telescope. Then here first, let me go back one slide. So all our instrumentation, so this is called a prime focus design. So here at the surface is the primary mirror of the telescope, and right here we have our secondary mirror and where the focus is, and then inside this cone is all our instrumentation, so all our receivers. So incoming radio waves hits the surface, it gets bounced up to the prime focus, so to the subreflector, and that gets reflected into our instrumentation. The Green Bank astronomy uses a bit more modern design. So instead of having a prime focus over here, the Green Bank astronomy and the Meerkat telescopes does exactly the same thing. We call this a off-center Gregorian design. So that means a bit of an oval shape. And here is our subreflector, and here is our equipment. So the reason why we went with newer designs is if we look at this image, here we can see the struts holding the subreflector in place, but these struts block a little bit of the surface area of our surface. So that means we're not using 100% of the collecting area of our telescope. Where in the Green Bank telescope, we can see there's an offset Gregorian, so one arm to the side, and we're not covering any of the surface area of the telescope. So that means we are using 100% of the surface area, meaning we are getting a better resolution with the telescope. So this was one of the coldest days outside. So this was back in 2019 when the polar vortex moved over the US. So this day was minus 27 degrees outside. So we actually had to stop observations on the Green Bank telescope because it was so cold. The oil inside the gearbox and the movable parts of the telescope actually became jelly, so cold it is. So therefore, when it becomes that cold, we need to stop observations in order not to damage the telescope. So this is an image of a modern spectrograph, or a spectrometer is another word for it. I prefer the word spectrometer. So this is what I'm using for my research. So this is called a FPGA, Field Programmable Gate Array. So you're all familiar with CPUs and GPUs. So CPU, standard component of your computer, and probably also the brain of your computer, and a GPU for graphics. But CPUs and GPUs are already too specialized to use for appropriate scientific work. Yes, you can use it, but it takes a hell of a lot of time to reprogram a CPU or GPU to do whatever you want, where FPGA, Field Programmable Gate Array, is a third type of processor that's not specialized. It's completely open source and open architecture. So you can use it for whatever you want, and you can actually specialize it into certain piece of equipment. So we use FPGAs to be specialized into a spectrometer. So this specific FPGA is called a Roach 2. So reconfigurable open source computing architecture. Very, very, very nice piece of equipment. So if we program this, create a firmware for it, and we actually hook it up to a telescope, here we can see a methanol maser sitting at 6.6 gigahertz that we can see. So this is an emission line coming from a maser. So maser is, all a laser, like the normal red laser pointers, green laser pointers. Lasers stand for light amplification by stimulation of emitted radiation. A maser is exactly the same thing. Instead of light, it emits microwaves. So it is microwave amplification by stimulation of emitted radiation. And these masers is basically a molecular cloud in space. It's usually in the region or in star-forming regions, or it's around stars that have shed off its outer atmosphere. So usually when we start detecting these masers, something happens, for example, in a star-forming region, and a high-energy particle moves through our molecular cloud, so maser cloud. That means the electrons in this cloud jumps from a lower valence orbit to a higher valence orbit that emits radio waves, and we can detect it. So this is the emission at 6.6 gigahertz, and from experiments in a lab, we know methanol radiates energy, or microwaves rather, at 6.6 gigahertz, so we know this is a methanol in space. So that is what spectroscopy is. But we will learn a lot more about spectroscopy in following chapters. And then we have adaptive optics in astronomy. So you've already learned about active optics, a technique to adjust the shape of the telescope optics slowly, compensating for effects of changing temperature as well, gravity bending the mirror when the telescope points at different locations in the sky. Adaptive optics is a more sophisticated technique that uses high-speed computers to monitor the distortion produced by turbulence in the Earth's atmosphere and rapidly alters some optical components to correct the telescope image, sharpening a fuzzy blob into a crisp picture. So you all are happy with the distinction between active optics and adaptive optics? Awesome. So in this image, we can actually see how it works. So here we can see the image on the left is where adaptive optics is turned off. And here the image on the right, we can see the difference when adaptive optics is turned on. Then we get to interferometry. So one of the reasons astronomers build big telescopes is to increase resolving power. And astronomers have been able to achieve very high resolution by connecting multiple telescopes together to work in a sense as if they comprised a single very large telescope. This method of synthesizing a virtual large telescope from two or more smaller telescopes is known as interferometry. So how this works in essence, instead of having one big telescope, we can spread the surface area into three smaller pieces. So we have our three smaller telescopes, and if we add the beams or the surface area of these telescopes, we get one big telescope. So the image on the left you probably all recognize as the VLA, the Very Large Telescope in the US that has 27 radio dishes. So you've probably seen this in a lot of sci-fi movies such as Deep Impact and a few others. And this is an array. So it is in a shape of an Y, and it's a part of the New Mexican desert. Then here on the image on the right is an image of the proposed SKA. Currently now it's the Meerkat, but the SKA has 64 dishes with roughly 12.5 meters diameter per dish, but that will become the SKA. So the SKA will, if you add all the surface areas of all the telescopes, then we have collecting area of 1 square kilometer. And then we get something interesting, non-electromagnetic astronomy. So other types of energy also arrive here bearing information from the rest of the universe. And that deserves a brief mention. And one is cosmic rays, or a subatomic particle traveling through space at tremendous velocities. Almost no cosmic rays reach the ground, but some of them smash into gas atoms in Earth's upper atmosphere, and fragments of those atoms shower down to the ground. Those secondary cosmic rays are passing through you as you read a sentence. Other types of particles from space interact weakly and shower them with Earth's atoms. So huge detectors must be built to catch and count them. Detectors for some kind of cosmic rays have been carried on balloons or launched into orbit, while others have been built deep underground. And do you all recognize this instrument? Yes, this is LIGO. Are you all familiar with LIGO? So LIGO is our observatory we use to detect gravitational waves. The Nobel Prize for Physics, I think in 2018 or 2019, was actually awarded for the discovery of gravity waves. So here we can see LIGO. We can see here a long, I think it's a bit long. And I'm not quite sure about the stats, but I think it's a mile long, and now another mile long in this way, so it's 1.6 kilometers. Works. So let me wait for the slide to appear on my side. So here we can see LIGO. So here we can see our, we have a laser beam. So we have a laser beam over here. And here we can see a beam splitter. So it will take the laser beam and split it into two. So the one is going down the pipe this way, one is going down the pipe that way. At the end, there are mirrors, and the laser beam is reflecting back. And we know the wave function of a laser beam. So if the laser beams are coming back in sync, meaning the two peaks are at the same place, then we know no gravitational wave has passed through. But if a gravitational wave has passed through one of these legs, that means our laser is not in sync anymore. Then we'll have a peak, for example, here, and the lower part of the wave, and these will actually cancel out. And that means a gravitational wave has moved through one of these legs. What is actually very interesting about these legs, these pipes, is so long that the curvature of the Earth actually starts playing a difference. So this must be, as long as it is, completely level, so that the curvature of the Earth doesn't interfere with it. So here, for example, in this illustration, we will have two black holes that's colliding. That will cause a gravitational wave. And sorry, it's not per mile, it's 4 kilometers long. So here, sort of on the graph, and when the gravitational wave moves through it, we can so this is the sweet and short of the LIGO Observatory. And ladies and gentlemen, do you have any question about this lecture? So, question. So, what would happen if two black holes collide? So, when two black holes collide, basically they will form one big black hole, but with the colliding process, you have two, it will cause havoc in the vicinity in terms of gravity, and that will cause gravity waves that we can detect. Sir, may you please explain the difference between active optics and other type of optics? So active optics is while the telescope is moving, you have those small mirrors, and you can create a big mirror, and you can essentially move all those mirrors to focus the telescope and get a clear image. So that means you are actively adjusting your telescope to get the correct image you are looking for. But in adaptive optics, you have your computers that while you are observing an object are adjusting the telescope on the fly or on the go. And that is called adaptive optics. So how do scientists know what they pick up via the gravitational waves? So if you look at this, the LIGO Observatory, so the only thing that can disturb these light waves to be out of sync if it's being affected by gravity, because we know gravity can bend light. So that's how we know it's a gravitational wave that moved through the observatory, and we detected the gravitational wave. Now, a question, are spectrometers used to detect organic compounds on other planets as well? So yes, that's what we're trying to use to look for other life on other planets. There's a few ways we can do this, but for example, if we look at a planet and we want to find out can it have possible life, we use a spectrometer to determine the atmospheric composition of that planet, and that will give us a better chance to say, okay, so it has the correct atmospheric composition, so there might be life on that planet. And then isn't gravity waves bending space? So yes, gravity waves is in essence bending space. Awesome. So we're going to start with our next set of lecture slides. So before we continue, let's take a 3-minute break, and we will continue this lecture at 6:40. So the laser coming out of some telescopes is used for adaptive optics. Yes, you are correct. And that laser we also use to calibrate the mirrors on. Okay, so a few questions. So repeat, sir, is it possible for light to travel at different speeds in different directions? No. So everything, light travels at the same speeds. There are a bit of physics that are investigating this. So I can saw someone is drawing on the image. Snitches get stitches. You guys are very funny. So I hear Google saying that laser is used to create an artificial star to improve atmospheric seeing. Can you elaborate? So I'm not quite sure what you are meaning with that, but I will see if I can find an article and try to explain it. So before we go on with our lecture slides, let me quickly show you another short video.
Enough through beautiful West Virginia, and you'll get to what is literally the quietest place in America. As you arrive, your phone will stop working, the radio will crackle out, and you'll find yourself in a place unlike any town in the world. Welcome to Green Bank. Population 150. Things to do? Not very many. But the research that takes place here could one day have a profound effect on the lives of all of us. The town is at the center of the US National Radio Quiet Zone. The rules are no mobile phone coverage, no strong Wi-Fi, nothing that might interfere with this, the Green Bank Telescope. Once a week, the telescope goes down briefly for maintenance. This was my chance to take in a truly incredible sight. It weighs more than 7,000 tons. It's bigger than a football pitch. It can rotate in a full circle, and it has a very important job. In the same way that an optical telescope is able to see far away into the universe, this enormous thing is able to listen far away.
The energy given off by a single snowflake is much greater than the astronomical signal that this telescope is trying to receive. They use 20% of the time on this telescope to specifically search for signals that may be coming from an advanced civilization. So if it happens, we're fairly certain that it will happen here first.
Back down on Earth, I meet Chuck. Locals call him the Wi-Fi police. I joined him on patrol.
Interesting.
It's Chuck's job to drive around Green Bank in search of interference that could be affecting the operation of the telescope.
It's looking for Wi-Fi hotspots, and then we've got a general purpose receiver that is really the main piece of equipment we use when we're looking for interference. Then we got a bunch of junk underneath here.
If you're thinking Chuck doesn't look like a particularly ferocious enforcer, you'd be right. In the battle of Chuck versus home Wi-Fi, the Wi-Fi has won. So now he just concentrates on the bigger signals. You'd think living here with all these restrictions on normal modern life would be irritating, quite hard to deal with, but there are some people who live in Green Bank, and it's precisely the reason why they're here. Diane is one of around 20 people who have moved to Green Bank because they feel they are essentially allergic to electronic interference.
Being near the cell tower, I had a headache. Being away from the cell tower, the headache went away. Returning closer, from a distance, the headache kept growing and growing and growing.
Shortly after I arrived, she asked if she could turn out the lights.
Add a little bit of
Dear guest, may these gifts to us be blessed, and please wisdom,
I used to multitask. I used to have a monitor here and I had another computer monitor there, and I could work those two things, and I would be listening to the radio, and I could do many things. But now, it's not something one wants to have. It's not something that one would pretend to have.
Diane has the full support of her family, but there are many out there that don't believe her condition is real. Regardless, she and several others see Green Bank not as a quaint American town, but as the last remaining safe place. But that peace and quiet could be under threat. The US government has said it may no longer be able to afford the upkeep of the telescope. Without it here, the legal protection for the quiet zone may no longer exist.
Starts off hour number one of something different for this Tuesday night here on Allegheny Mountain Radio.
Despite the restrictions, the town does have a radio station that broadcasts on a frequency that does not interfere. For a sense of how the town may change if the telescope was to go, I popped in and found a friendly face.
Set short. There's some people would be just over the moon happy that we'll finally get cell phone service, but it's not going to change the fact that you can't put up a TV antenna unless you're up on a high mountain and pick up some local TV station.
If you talk to the middle school kids, especially in Green Bank, they definitely wish that they did have cell service.
Back at the observatory, I'm told how they've rebranded in an attempt to court private investment. And while rather out of the way, there's ambitions that one day Green Bank could be a tourist destination. Eventually, they hope it can sustain itself even without government help. Coming here and seeing this great big thing, it really makes your imagination run wild. I mean, what if they were to hear something? What if they were to hear that aliens are out there communicating, perhaps even communicating with us? It would change everything, I think. So if you want them to keep on listening in that thing over there, then I suggest you try and visit Green Bank. I can promise you it's worth it.
How many of us have walked out into the night and looked up at the stars and stood there in wonder? We don't produce widgets. We don't produce something that you go to the store and buy. But we do produce education. We do produce research. We do produce answers to questions that we haven't even asked ourselves yet. And that thirst for knowledge is why a facility like this exists and why it must exist in the future. Those questions are the basis of what it means for us to be human. And that constant search is done here every day. I don't know how else to put it.
So Green Bank is a very, very cool place. So I just saw here, Mr. Alec, you had your hand up. Okay, no problem. So one thing you notice at these observatory, you will get the scientists, your extremely smart people, and then you will also get your weirdos at the observatory itself. So there's usually a joke going around. So the population of Green Bank is more or less 150 people. From that 150 people, 110 work at the observatory. And from that 110 people, about 94 have PhDs. So if you look at a Guinness Book of Records, Green Bank is the most educated town in the world. But there's also a joke in Green Bank that's circulating that says Greenbank is the place where cocktail parties meets moonshine orgies, because it's in rural West Virginia. So that's just a little joke going around. But it is a awesome, awesome, awesome place to be. So let me open up the next set of lecture slides. So for this lecture, we are going to start looking at atoms and spectra. So let me ask you guys this. Can you define spectra for me? Any volunteers, any ideas? So yes, you can call it a scale or a range. So electromagnetic waves, but yes, the spectra of electromagnetic waves is if you split up the electromagnetic waves into its different components, what components do you actually see and detect? So for this lecture, we're going to look at atoms and spectra, atoms, a model atom, different kinds of atoms, interactions of light and matter, the excitation of atoms, radiation from a heated object, understanding spectra, chemical composition, and finally measuring velocities, so the Doppler effect we can see in spectra from objects. Awake, for the morning in a bowl of night, has flung the stone that puts the stars to flight. And lo, the hunter of the east has caught the Sultan's turret in a noose of light. In a previous chapter, you learned how telescopes gather light, cameras record images, and spectrographs spread light into spectra, so plural form of spectrum. Now you are ready to understand why astronomers make great efforts to gather and analyze spectra of the objects of the sky. So whoever is writing on the slides, can you please ask you to stop writing on the slides? So in this lecture, we are going to answer 3 fundamental questions. So firstly, how do atoms interact with light to produce spectra? Secondly, what are the types of spectra you can observe? And then last, what can you learn from spectra of celestial objects? In this chapter, you will begin using modern astrophysics, linking astronomical observations to physics observations and theories, to investigate secrets that lie beyond what you can see directly. So through a spectrometer, or spectrograph, depending which word you like to use. So we usually use a spectrograph with an optical telescope, spectrometer with a radio telescope, but they are basically the same things. So this is a spectrum of optical telescopes. So here we can see our peaks in the spectrum. These are emission lines. So if we look at this, so here we can see the different colors that's actually being emitted. But what we will see through our instrumentation is these peaks corresponding to certain wavelengths, and this is a nanometer, and a certain wavelength has a certain color. In this chapter, you will begin using modern astrophysics, linking astronomical observations to physics observations and theories to investigate secrets that lie beyond what you can see directly. The universe is populated with brilliant stars, illuminating exotic planets and fabulously beautiful clouds of glowing gas. but beyond members of our tiny local solar system, they are all out of reach for the foreseeable future. No human space probe has visited another star. A new telescope and no telescope can directly examine the insides of any celestial object. Information you can obtain about most of the universe is contained in the light reaching you across space. So here we can see on the left a nice visual image of the Carina Nebula, and on the right an infrared image of the same nebula. And that is why it is important that we have different telescopes looking at different parts of the electromagnetic spectrum, so we can see features from the object we're looking for. So here we can see the gas clouds of the nebula is actually blocking the view of the stars, and you can see some of the stars in the part. So this is so if some of you are struggling to hear me, is this better now? Okay, cool. So the earth-bound humans knew almost nothing about the composition of celestial objects until the early 19th century. First, the German optician Joseph von Fraunhofer studied the spectrum of the sun and discovered that it is interpreted by more than 60 dark lines, representing colors missing from the sunlight Earth receives. So here we can see the solar energy distribution or the spectrum from the sun. So here we can see UV, visible light, and this is near infrared. So here we can see different peak. So here we can see the solar radiation curve. 5% is ultraviolet, 43% is visible light, and 52% is near infrared. But here we can see incoming solar radiation at sea level, and here we can see the yellow parts shows energy absorbed by gases in the air, including water vapor, carbon dioxide, ozone, and other greenhouse gases. The other scientists performed laboratory experiments showing that those spectral lines are related to the presence of various atoms in the sun's atmosphere. Finally, astronomers observed that the spectra of other stars have similar patterns of lines, which opened a window to real understanding of how the sun and stars are related. The atoms in stars and planets leave their fingerprints on the light they emit. By first reviewing what atoms are and then learning how they interact with light, you can understand how the spectra of objects in space are decoded. So here we can see how we normally represent an atom. So we have the nucleus. The nucleus has a proton and a neutron, and we have an electron orbiting the nucleus. But this representation is actually wrong, but it's a nice idea to imagine an atom. To think about how atoms interact with light, you need a working model of an atom. In this chapter, you will begin your study of atoms by creating a mental model of an atom. Remember that such a model can have practical value without being true. The stars are not actually attached to a sphere surrounding Earth, but to navigate a ship or point a telescope, it's helpful to pretend they are. The electrons in an atom are not actually little beads orbiting the nucleus the way planets orbit a sun, but for some purposes, it is useful to picture them as such. The model atom contains a positive charged nucleus at the center, which consists of two kinds of particles. Protons carry a positive electrical charge, and neutrons has no charge. That means that a nucleus has a net positive charge. The nucleus of the model atom is surrounded by a cloud of electrons that are low mass particles with negative charges. Normally, the number of electrons equals the number of protons, and the positive and negative charges balance to produce a neutral atom. A single atom is not a massive object. A hydrogen atom, for example, has a mass of only 1.67 times 10 to the minus 27 kilograms, about a trillionth of a gram. Protons and neutrons have masses almost 2,000 times greater than that of the electron, so most of the mass of an atom lies in the nucleus. An atom is mostly empty space. To see this, imagine constructing a simple scale model of hydrogen atom. Its nucleus is a single proton with a diameter of approximately 1.7 times 10 to the power minus 15 meters. If you multiply this by a trillionth, so 10 to the power 12, you can represent the nucleus of your model atom with something about 1.7 millimeters in diameter. The region of a hydrogen atom that contains the electron has a diameter of about 0.24 nanometers. Multiplying by a trillion increases the diameter to about 240 meters. So, common misconception. Most people, without thinking about it much, imagine that matter is solid. But now you understand that atoms are mostly empty space. The chair you sit on, the floor you walk on, are mostly not there. So here we can imagine this. A magnifying hydrogen atom by a trillionth makes the nucleus the size of a grape seed, and diameter of the electron could be more than 2 times larger than a US football field. So here we can see this visualized, the size of a football field. So if we enhance an atom with a trillion, we can see the nucleus will be the size of a grape, and the electron spin, or the electron orbits, will be far outside the reach of the atom, so bigger than a football field or rugby field. There are over 100 chemical elements. The number of protons are in the nucleus of an atom determines which element it is. For example, a carbon atom has 6 protons in its nucleus. An atom with 1 more proton than its nitrogen, and an atom 1 fewer proton is a boron. Although an atom of a given element always has the same number of protons in its nucleus, the number of the neutrons is less restricted. For instance, if you added a neutron to a carbon nucleus, it will still be carbon, but it would be slightly heavier. Atoms that have the same number of protons but a different number of neutrons are isotopes. Carbon has 2 stable isotopes. One contains 6 protons and 6 neutrons for a total of 12 particles, and this is called carbon-12. Carbon-13 has 6 protons and 7 neutrons in its nucleus. The number of electrons in an atom of a given element can vary. Protons and neutrons are bound tightly into the nucleus, but electrons are held loosely in the electron cloud. So you're all happy with this definition of isotopes? Awesome. So see a few of you are complaining about audio. I just look at the stats because I have a bit more control over Blackboard Collaborate. So it seems like there's a bit of an issue with Blackboard this evening. Looks like we are not the only ones struggling with this. I don't know why, but just bear with me another 10 minutes, and then hopefully next week it will be better, but I will ask the university what's happening with Blackboard. So running a comb through your hair creates a static charge by removing a few electrons from their atoms. An atom that has lost or gained 1 or more electrons is said to be ionized and is called an ion. A neutral carbon atom has 6 electrons that balance the positive charge of the 6 protons in its nucleus. If you ionize the atom by removing 1 or more electrons, the atom is left with a net positive charge. Under other circumstances, an atom may capture 1 or more extra electrons, giving it a more negative charge than positive. Such a negatively charged atom is also considered an ion. Atoms that collide may form bonds with each other by exchanging and sharing electrons. Two or more atoms bonded together form a molecule. Atoms do collide in stars, but high temperatures cause violent collisions that are unfavorable for chemical bonding. Only in the coolest stars are the collisions gentle enough to permit the formation of chemical bonds. The presence of molecules such as titanium oxide detected in some stars is a clue that those stars are very cool compared with other stars. Electrons are bound to the atom by the attraction between their negative charge and a positive charge on the nucleus. This attraction is known as the Coulomb force. To ionize an atom, you need a certain amount of energy to pull the electron completely away from its nucleus. This energy is the electron's binding energy, the energy that holds it to the atom. The size of an electron's orbit is related to the energy that binds it to the atom. If an electron orbits close to the nucleus, it's tightly bound, and a large amount of energy is needed to pull it away. In other words, its binding energy is large. An electron orbiting further from a nucleus is held more loosely, and less energy is needed to pull it away. That means it has small binding energy. Nature permits atoms only certain amounts, so quanta, of binding energy. The laws that describe how atoms behave are called the laws of quantum mechanics. Because atoms can have only certain amounts of binding energy, your model atom can have orbits only of certain sizes called permitted orbits. These are like steps in a staircase. You can stand on number 1 step or number 2 step, but not on number 1 and not on number 1 and 1/4 step. There isn't one. The electron can occupy any permitted orbit, but there are no orbits in between. The arrangement of permitted orbits depends primarily on the charge of the nucleus, which in turn depends on the number of protons. So here in this image we can see an electron in an atom may only occupy a certain permitted orbit. Because each element has a different number of protons, and therefore a different electrical charge in the nucleus attracting the electrons, each element has a different unique pattern of permitted orbits. So here we can see hydrogen nuclei have just one positive charge, so the electron's orbits not pulled close to the nucleus. So here we can see the orbits. So helium nuclei have 2 positive charges. Only the innermost electron orbits are shown in these 3 examples. And then boron nuclei have 5 positive charges. So the electron orbits are tightly bound to the nucleus. So here we can look at the orbits more closely. So here we can see our nucleus. Here we can see the orbit, so we can call this different shells. And each shell has a different energy level. So how does this actually look? So we all saw the image we had in our opening part of this chapter. But this is actually how it will look like. So here we can see the blue part are the electron shells. The green part is the electron orbit. And the red part is the insulating magnetic field. Because we have moving electrons, it will induce an electric field. And then we are all familiar with the periodic table of elements. And the periodic table of elements is a nice way to describe how much electrons, protons, and neutrons we have in our different atoms. So where would be the s orbital? The s orbital of what? So it all depends on the atom we are looking at. But yes, so it's hard to visualize actually how it would look like, but this is a nice simulation of how it actually will look like. So the next part is interactions of light and matter. So ladies and gentlemen, I think we will call this for tonight. So we will continue on this lecture in next Monday's class. So I hope that you all enjoy this lecture. Good luck with the rest of the week, and I will see you all next week, Monday. I will remain active for another minute or two if you have any questions. Otherwise, have a wonderful evening and good luck with the rest of